So it's my pleasure to be with you with the SPIE student chapter in IISER Kolkata. And I'll discuss applications of silicon photonics in life science and medicine. I have an Indian co-worker and she helped me to make this slide, which, if I understand well, is in Bengali. So let me introduce the field, but let me talk a little bit about my own activities and my own lab, etc. for a few minutes. First of all, I'm in Belgium and I'm in the city of Ghent. Belgium is this tiny country in Europe. Ghent is this city here. Let me switch perhaps to the laser pointer. Ghent is this city sort of in between Brussels, the capital of Belgium, and the North Sea. It's a lovely city, so if any of you ever have the opportunity to visit Ghent, don't hesitate to do that. You will enjoy it. You will always be welcome to visit us. About the research group of which I'm part, this is the Photonics Research Group. It's a research group of Ghent University, of course. We're in the Faculty of Engineering and Architecture, Department of Information Technology. Something special about this is that we are a so-called associated laboratory of IISER. I'll touch upon that in a minute. And member of a university-wide Center for Nano and Biophotonics. What we are focusing on in our research is really photonic integration, which really means to build photonic systems on a chip. And we do that mostly with the technology of what is called silicon photonics these days. But it's not all about silicon at all. Actually, in silicon photonics, there's a lot of emphasis on enriching silicon chips with a variety of new materials, heterogeneous integration to enable new functions. And all of that is enabling a rather broad variety of applications, high-speed telecom and datacom being the most prominent one, but also a lot of different sensing modalities, and part of that is for medical devices. And finally, also optical information processing. We are a fairly large group, as you can see from the picture here. We are close to 100 people actually, 9 professors, close to 20 postdocs, about 50 PhD students, and some support staff, of course. It's a very international group. Several of the professors have received European Research Council grants, which in Europe are sort of the most prestigious grants you can hope for. We are doing research, but we also try to help in innovation in the sense of spinning out companies. And I should also, last not least, mention that we are running here at university a Master of Science program in the field of photonics. Let me also mention that we continuously and also now have vacancies both at the PhD and at the postdoc level. Feel free to visit our website to see the details. One more word about Ghent University. Ghent University is a relatively old university, well, just over 200 years old. It was founded in 1817. At that time, Belgium was actually part of the Netherlands, and so we were founded by the King of the Netherlands. Ghent University is a top 100 university. It's located in Flanders. The local language here is Dutch, same language as in the Netherlands. At the bachelor level, we do teach in Dutch, but at the master level and onwards, everything is in English. I also mentioned IISER, and actually on each of my slides you see 2 logos. One is the university logo, the other one is IISER. IISER is a large R&D facility in Belgium, focusing on nanoelectronics and digital technologies. It's several thousand people. It's very international, of course. This is a picture of the campus of IISER. It's in Leuven, which is just east of Brussels, where you have both a wafer fabrication fab, both for 200 millimeter wafers here and for 300 millimeter wafers here. And that is relevant in my talk because I'll be talking about silicon photonics, meaning chips, and chips come out of wafers, and in these wafer fabs, this is where most of our wafers are being manufactured. Okay, that as a short introduction, let me emphasize that for this talk, I would hope to be as interactive as is possible given this online setting, but feel free to ask any question or give any comment during the talk already. You don't have to wait for the end of it. Please use the chat. I have the chat open in front of me, so I'll keep an eye on it. So I'll, whenever I see questions popping up, I'll try to address them during the talk. Okay, so this talk is about applications in healthcare. So a few generalities here. Just about everywhere in the world, we have aging societies, certainly in the Western world. It's ever more difficult to keep performant healthcare affordable for society, not for the happy few, but also for all of the population. And as we know, since a little more than a year, pandemics also present quite a challenge. It can have an enormous impact. And I know you're suffering in India, but also in Europe, we are suffering badly and are now here in Belgium, we are sort of in a third wave at the moment and are trying to mitigate that third wave as we speak. So in all of this, and given these challenges, technology is not everything, but technology can definitely help for performant healthcare, which is affordable. You think in terms of low-cost medical devices, personal devices, bedside devices, point-of-care devices. So I'm rather not talking about the sophisticated machines you find in sophisticated hospitals and medical laboratories, but rather about what you can do in your own home, at the GP's office, etc. Also, I'm talking about minimally invasive devices that can be about catheter approaches, implants, electronic pills, where small is beautiful, obviously. And I'm also talking about rapid diagnostics, such as, for example, immunoassays based on disposable use once chips. I'll also touch upon that. So this is a bit the context of this talk. The technology that I'm talking about is chip-based silicon photonics, as I'll discuss in a minute. But more generally, the usage of microchips is actually quite dominant in the field of medical devices. Think of well-known examples such as pacemakers full of electronic chips. In the past year, those infrared fever thermometers have become quite popular. They're essentially measuring thermal radiation from the body's skin. That is radiation in the 10 micron wavelength range. So for that, you use mid-IR detector chips. And of course, everybody knows this little device, the pulse oximeter, that is used massively in hospitals since a couple of decades. And essentially, it's a chip-based device. It simply sends light from simple LEDs through the finger onto detectors, and from that can determine the saturation level of oxygen onto the hemoglobin in the blood. So these are simple examples, well-known examples where chips make the difference, and the way chips, the fact that chips are used is quite important, because chips, when manufactured in volume, become very cheap. And therefore, the three devices that you see here are actually quite affordable devices. Actually, devices such as this pulse oximeter and also the fever thermometer. These are devices that are being sold for a couple of tens of dollars. The pacemaker is probably a bit more expensive because it's an implant device, of course. Okay, let's move to silicon photonics. What is silicon photonics? Well, it's quite simple. The world has invested for the past 50 years massively in silicon technology for the electronics world. We have microelectronics, nanoelectronics, and we have these technologies where on wafers of 8 or 12 inch, 200 or 300 millimeter, very sophisticated electronic circuitry is being made. think of a microprocessor these days. That's a device with a few billions of transistors sitting on a few square centimeters, and it works amazingly. Well, silicon photonics builds on this technology heritage. It uses the same technologies, the same machines, the same fabs, but it doesn't make electronic circuitry, it makes photonic circuitry. And for example, what you see here, it doesn't really look like an electronic circuit. It is not an electronic circuit, it's an optical circuit. This actually contains circuits to sense glucose from blood. But this photonic circuit is made from exactly the same type of materials and technologies as is the case for transistor circuits in electronics. So the big value offering of silicon photonics is that you can piggyback on insanely mature technology, which is, in terms of the fabs and the technology and the infrastructure, extremely expensive, but paradoxically, at the end of the day, the chips that come out of these fabs are insanely cheap. And with that, we can now enable complex optical functionality on a compact chip at low cost. And that is the essence of the story of silicon photonics. 20 years ago, silicon photonics was still very much an academic field. 10 years ago, we saw the emergence of commercial usage of the technology. And today we can say that really there is a lot of momentum behind this technology, and there is industrial activity gearing up to high volume applications. A few more words about the technology. Well, first of all, if you want to make circuits for light on a chip, you of course need a wire for light. And the wires for light we use on these photonic chips are these, we call them photonic wires. They are optical waveguides, similar to an optical fiber, but then on the surface of a wafer, and actually much smaller than an optical fiber. So you see this strip here. It's a strip of silicon with its refractive index of about 3.5. Surrounded by silicon oxide with its refractive index of about 1.5. So this is a dielectric waveguide. It's a waveguide that can guide light, at least in the wavelength range where silicon is transparent, which is in the infrared. The index contrast between silicon and silicon oxide is very high, and that means that you can make very compact circuitry. You can make very, very sharp bands, and at the end of the day, chips become very small, which means that you can have several thousands of chips on a single wafer. And not only can you make these simple waveguides, of course, that would be a bit boring, but then you can combine that with other photonic functionality. There is modulators, there is detectors, there is wavelength selective functions, there is polarization sensitive functions, and so on. The only function that is a bit more difficult on this chip is the integration of light sources. But now there are heterogeneous integration ways of combining other types of semiconductors, like 3-5 semiconductors, onto silicon, by which we can integrate light sources just as well on such a silicon chip. So, and with that combination of functions and materials, you can build systems. You can build a system such as a transceiver, and that is actually quite popular in data communication, for example, in data centers, and also for telecommunication, long distance fiber communication, where these days you have typically these little boxes here, a bit the size of a USB stick, where essentially on one hand you have electrical signals coming in, and on the other end there is an optical fiber coming out. And there is essentially a conversion from electrical signals to optical signals, or vice versa. It's a transceiver. And today, typical data rates are 100 gigabit per second at a simple rate of perhaps 25 gigabaud in various modulation formats. And under development at the moment in research labs is even data rates that go all the way up to something like 800 gigabit per second, moving from electrical to optical in such a small device. Obviously, these are the little workhorses in data centers where you will find not just tens or hundreds, but many thousands or 10,000s of such transceivers. And you see here just all sorts of logos of companies that have industrial activity in this field to build such silicon photonics-based devices. Now, this is not what I'm going to talk about here. I'll move to sensing. And before doing so, I should mention that while the normal silicon photonics waveguide has a core of crystalline silicon sitting on a buffer layer of silicon oxide, with which you can address a wavelength range somewhere between just over 1 micrometer up to just over 3 micrometer. That's the transparency range of a silicon waveguide. This edge here corresponds with the band gap of silicon. So below that, silicon is absorbing, and the other edge relates to where silicon oxide becomes absorptive. So in between, there is this window where both silicon and silicon oxide are transparent. Now, in quite some applications, you're not happy with only using that range. You may want to move to shorter wavelengths and all the way into the visible range of the light spectrum. But then actually you can use a variation on a theme, which you can also do in an electronic CMOS fab, whereby you replace the core of the waveguide, which here was silicon, you replace it by silicon nitride. Or you can move further down into the mid-infrared, in which case you have to replace the silicon oxide. And here is one popular arrangement where you have a waveguide of the semiconductor germanium sitting on a layer of silicon, which is a waveguide in the mid-infrared. So you see there are some variants in the field of silicon photonics, and together they cover anything from the UV here, the UV starts about here, all the way to beyond thermal radiation beyond 10 micrometer. Okay, why would you want to use silicon photonics for medical devices and for healthcare in general? Well, first of all, there are a couple of good reasons here. There is really a rich set of sensing modalities, and I'll touch upon that later in the talk so that will become clear. But obviously, very importantly, by doing it by means of silicon photonics, you move to a situation where chips are really very low cost, and therefore you can hope to make very performant devices at quite an affordable cost. Even up to the point where some of the devices, and that is the case for immunoassays, for example, where the devices become disposable, use once chips. So the chip is only used once. You put a drop of blood on it, for example, and it's used for the analysis of one person's blood one time, and then it's no longer used. So the technology is really allows to do this. A small silicon photonics chip produced in mass volume can have a cost of a small fraction of a dollar. I already mentioned you can make very compact devices, and you will understand that that is quite important if you think in devices that have to become bodily implants, for example. You can go through this very broad wavelength range from visible to mid-IR. And last not least, you can already build on a very mature supply chain. CMOS fabs exists, and you can tap into that capacity. Okay, if we bring a bit of structure in that whole field of medical devices based on silicon photonics, we can sort of distinguish 4 classes of devices. And I'm putting them on 2 axes here. And both axes are the axis where silicon photonics is really good at. There is the axis of size. So small size matters. The more you go to the right, the more small size really matters. And then there is here the vertical axis where I put low cost matters. At one end here you have the in vitro diagnostics. That is really the field of use once chips, disposable chips. So quite obviously, you have to use chips that are very, very low cost to come to that regime. At the other end, there's these catheterized devices and smart pills and also wearables, including implants. This is obviously a field where small size really matters. And somewhat in the middle, you have all sorts of point-of-care devices, devices that a general practitioner will be using or a nurse will be using, and where you typically think in terms of handheld devices that are quite affordable in cost. Okay, let me start with probably the most common type of device based on integrated photonics in the medical field. That's the biosensor. It's called also label-free biosensor. It's a refractive index sensing device based on antigen-antibody binding. What really happens is that you have this device. This is a so-called ring resonator. Here you see an electron microscopy picture of such a ring resonator. You have an input waveguide here. Light comes in here, but then passes very close to this ring waveguide, close enough so that part of the light will couple to the ring. Light will circulate in the ring. It's a resonator. Part of the light will couple out from here, and the rest of the light will couple out from here. This is a resonant device. If you measure the transmission from this input to this output, you find, as a function of wavelength, you find these sharp resonant peaks, and further down the wavelength axis, this repeats itself several times. Now, the point is that if you functionalize the surface of this ring with these antibodies, for example, and if then you have a microfluidic system and you bring the chip in contact with a fluid containing the antigens that can bind by an affinity chemical binding to the antibodies, then of course, by that selective binding process, you create a thin extra layer on the waveguide surface that changes the so-called effective refractive index of the waveguide. And with that, the resonance wavelength shift will shift over a small spectral distance. And that shift is something you can easily read out. So basically, the sensor is doing nothing else but reading out a resonant wavelength shift. But of course, what you are sensing is the very selective binding of one type of protein to another type of protein. And because that is selective, the overall sensor at the end of the day is also selective. In general, for this type of biosensor, two types of devices are very popular. One is, and I already discussed this, one is this micro ring resonator, input light, some light coupling to the resonator, and then coupling out again, and there is often a second waveguide sitting at the other side, with functionalization at the surface, of course. That's one type.
Excuse me, sir?
Yes.
It's when the previous figure there was a. So how do you are changing this lambda? How you are changing this lambda?
Well, that's a readout thing. What you really want to do is the spectral transmission from this input to that output. You want to measure that as a function of wavelength. In general, you can do that in two ways. Either you excite this waveguide with a wavelength tunable laser, and at this output you put a simple detector, and then all you need to do is you really go with the laser wavelength through this wavelength axis, and you monitor what the detector is saying. So you time sequentially you measure this spectrum. That's one way to do it. But probably the more common way to do it is to send broadband light, white light, so to say, into the ring resonator. And at the output here, you then form a spectrometer. You disperse different wavelengths at the output to different detectors. And with that, you can also measure a spectrum. It's all based on measuring a spectrum of light. Okay. And I think in most practical implementations, certainly the commercial application, it's mostly the second approach that is being used. During research, one is often using tunable lasers, but tunable lasers tend to be more expensive. Therefore, they are less practical in commercial devices. Okay. Okay. So these are the two types of devices. And in each case, of course, you have to functionalize the surface so that it can selectively bind to certain biomolecules or bio-objects. Actually, and perhaps let's discuss a little bit about diagnosis of viral infection, because that is now so important in this world. Think indeed of a coronavirus. And actually, there are several strategies that are possible for viral infection diagnosis. One thing you can, and all three can be done with the same optical biosensor in principle. The first thing you can do is to do really a genomic detection. You really make sure that the viruses that come along are broken down so that they release their DNA load. And you make sure that the surface of the chip is functionalized with short stretches of nucleic acids. And of course, then you will have the typical thing that happens is that a single strand DNA will be able to bind selectively to its complementary single strand of DNA. And with that, you can basically detect whether certain sequences of nucleic acids are present in the virus. So this is actually very similar to the PCR test that is now very popular for diagnosis of COVID-19. So that's the first strategy. A second strategy is that you would say, why not try to detect the virus itself without breaking it down as a whole? In that case, you need to functionalize the surface of the chip with antibodies that will bind to what in this case is then called the antigen, being the virus itself, and more specifically to the spike proteins that you find on the surface of the virus. They have their fingerprint three-dimensional structure, and that can selectively bind to also a kind of complementary structure, being the antibody on the surface of the chip. And in that case, you really bind individual virus particles onto the chip. And a typical COVID-19 virus has a diameter of something like 89 nanometer. So you create an extra layer of course, it's not probably fully densely populated, but you create a layer with particles of 80 nanometer diameter on the surface of the chip. And then there's the third strategy, which is a blood assay, a serology assay, where basically you're not testing for the presence of the virus, but you're testing for the immune reaction of the body. That's what the body is supposed to do when it is attacked by a virus. It should create antibodies. It should create things like this green thing in the body so that afterwards, when the virus tries to attack again, these antibodies can hook up to that virus and mitigate its further action. So in the third case, you want to detect those antibodies, which means you need to functionalize the surface of the chip with antigens in this case. So things that resemble the spike proteins of the actual virus. So it's the other way around from here. So in this case, you're not detecting for being infected. You're diagnosing for having been infected once upon a time in the past, because you're detecting the antibodies. So these are sort of the three strategies that you can have in biosensing, and all three can be done with this refractive index sensing on a silicon photonics platform. And actually, there are already several commercial examples of this. This is the example of Genelite. That's a company in California. They have been working for more than 10 years now on silicon chip-based photonic ring resonators. So they use these silicon photonics ring resonators together with a readout device. So this is mostly for laboratory use. And indeed, they have, over the past years, they have developed a serology test. So it's of the third type. So they functionalize their chips with antigens and then test for antibodies in somebody's blood. And it seems to work extremely well. Here is another example. This is actually an example from a spin-off company of our own group here in Ghent. And here, this is an interesting example because here the idea is really to develop a use once chip, which will be tested by a simple readout device for home and point of care use. So no longer in a central lab of a hospital, but rather you go to the pharmacy, you buy this, and you do this at home. Their first product they are bringing to the market is a self-test for sexually transmitted diseases from urine. But now they are, actually just yesterday, there was a public announcement that they also have been developing a COVID-19 and a flu self-test based on this technology. So again, this I think is quite a relevant development because indeed the cost of these devices is very low, and you can go to the pharmacy, buy it for quite an affordable price, and do the self-test yourself. I should mention before moving on that these refractive index sensing sensors, I discussed them in the context of biosensing, but actually you can use them for many other types of sensing, as long as you can translate some physical or chemical quantity into a refractive index change. And we have been doing some work on using it for gas sensing, where basically you recognize here again this Magzener interferometer chip, and one of both arms is exposed to a gas. And actually, in this cross-section, you see that in this case, the waveguide, in this case, it's a silicon nitride waveguide, it is actually surrounded by a porous silica material with very, very tiny pores, but of course still large enough so that the gas can easily penetrate in the pores, and such that the gas molecules will be absorbed to the massive amount of walls you have in a porous material. So essentially, this porous material is a density amplifier. Outside, there is the gas with its rather low density of gas molecules, but because the gas enters into the porous structure, absorbs to the walls of the pores, you get in the porous material and several orders of magnitude higher density of molecules than in the gas phase. And of course, that higher density in that cladding will translate into a higher refractive index, and that will again lead to a shift of the interferometric spectral spectrum of the Magzener interferometer. Indeed, Magzener interferometer has these dips in the transmitted power, and those dips as a function of wavelength will shift, just like in the case of the ring resonator. And with that, we could actually detect various gases, vapors with quite low concentration, almost trace gas detection. For example, acetone with a limit of detection of something like 65 ppb. Ethanol, even limit of detection of 1.6 parts per billion. So extremely sensitive gas detectors. Okay, so the biosensor is for sure the most prominent integrated photonics device entering the healthcare sector. But in the remainder of the talk, I'll be talking about a few other examples, but perhaps let's take a very, very short break to see whether there are any questions. I don't see anything in the chat right now. Any questions from the audience right now? Also, feel free to just speak up. If not, I'll move on, and I'll be discussing in the rest of the talk three modalities of sensing for medical applications that are at the moment still more in the R&D phase, although some of them are already being prepared for commercial products. I'll start with CGM, continuous glucose monitoring, and I'll move to a cardiovascular application, and I'll finish again with in vitro diagnostics, but now with a modality that is different from refractive index sensing because it's based on Raman spectroscopy. And given that I'm talking for an Indian audience today, I thought I should have also this Raman application as part of this talk. Okay, first application, glucose monitoring. Obviously, the context is diabetes. Diabetes is really another, it's also often called a pandemic because the rate of prevalence of diabetes is alarmingly high and increasing quite strongly. Estimates are that today about 1 out of 12 people is suffering of diabetes, and that fraction is unfortunately increasing rather rapidly for reasons that are not fully understood. So it's a huge thing, diabetes. It's also a disease without a cure. The only thing you can do is try to you can't cure it, but you can try to control its impact. But to control its impact, you need to know continuously what the glucose levels in your body are. And one measurement a day is not sufficient because now and within an hour from now, the levels can already be very different in a diabetes patient. So the technique that we are using for measuring glucose concentration in blood or in tissue is based on absorption spectroscopy. Well, here I'm just showing that indeed levels of glucose in the body in a healthy person, they obviously also change over the day because you're eating and drinking, etc. But in a diabetes patient, that variation of glucose level is wild. It goes to low hypoglycemia, it goes to high hyperglycemia, and both hypo and hyper are actually quite bad for the body. So it's all a matter of measuring the glucose level and then reacting fast enough so as to mitigate the damage done to the body. The physical principle that we are using to measure glucose is optical absorption spectroscopy. If you look at as a function of wavelength, this is a range from 1550 nanometer to 1800 nanometer. And this is another range just beyond 2000 nanometer. And you do indeed see that glucose has these broad absorption features. And indeed, of course, if you go from lower to higher concentration of glucose, obviously the absorption becomes more prominent. The problem is that given the physiological concentration of glucose in the body and taking into account a reasonable measurement distance, the change of transmitted light power is actually very, very, very small. And on top of that, blood with glucose is not water with glucose. In blood is quite a rich mix of all sorts of molecules. And apart from glucose, there is also a high concentration of lactate and of ureum, etc. So you have all sorts of molecules, and unfortunately, all of these organic molecules have absorption features which heavily overlap. So that makes it actually a tough problem. The only way you can deal with that toughness of a problem is to measure over a sufficiently broad wavelength range, not just over 50 nanometer or something, but measure over several hundred nanometers. Then you can hope to unambiguously determine the level of glucose. But that's exactly what we did with our silicon photonics chips. The concept, simple, you have these waveguides. You should realize that when light travels through an optical waveguide, the light is confined to the core, but not for 100%. There is always a little bit of tails of light sitting outside the core of the waveguide, sitting into the cladding. So if that cladding is then a fluid containing glucose, then indeed you have interaction between light being guided in the waveguide and that fluid with its glucose. And that's exactly what we do. You need some sort of microfluidic system so that the surface of the waveguide is covered with the fluid, and with that you can hope to see light being absorbed by that fluid. And then, of course, on that same chip, you can build in extra functionality, the light sources, the spectroscopy devices, and the detectors. So this is work that dates back more than 5-6 years now, where indeed we made this silicon photonics chip And it contains indeed the light sources and then the spectrometers, the detectors, etc. And we bring in tubing so that we can flow fluids onto the chip. And the first proof of concept was just to send water with glucose through the chip. And indeed, you see here an experiment where we saw an extremely nice and clean correspondence between the applied glucose concentration measured separately and the glucose concentration extracted from the spectral absorption measurement on the chip. And we demonstrated the sensitivity of the order of 1 millimolar, which is more or less what is needed clinically to measure glucose in diabetes patients. We as a research group haven't taken it much further, but then we spun out a company, it's called Indigo, which took this, this basic same technology further. All of this with a mindset of building an implant device. And here you see one of their prototypes. It's a small coin-sized device and rather thin. You see here the size of it, which can easily be implanted just under the skin subcutaneously with a very simple surgical procedure, and will for a year or two measure continuously the level of glucose in the surrounding tissue. And of course, the device is powered through RF induction and will also exchange data by RF communication with, for example, this readout device, which then communicates with your smartphone, etc. And indeed, the core of the device is a microspectrometer chip. You see a picture of that microspectrometer chip that is doing the job of measuring glucose. Actually, here you see results from this device, not yet on humans. This was on a pig model. For some reason, the way a pig is dealing with glucose seems to be similar to how the human body is doing it. So pigs are very popular in this research. But indeed, you see this beautiful Clark grid, as it is called, which indeed shows, and this is not in water, this is really in blood, of course, or in tissue, which shows the correspondence between the applied glucose concentration measured independently with the extracted glucose concentration extracted from the spectral measurement on chip. And you see a very nice correspondence across many different situations, different pigs, different times of the day, before eating, after eating, etc., etc. This company is now moving to a round B investment, and actually just a few weeks ago they announced publicly that they have initiated their first clinical study on humans, so as to move the device to the market. So quite a relevant development, I would say, for the millions and millions of diabetes patients, well, hundreds of millions of diabetes patients around the world. Okay, so this was absorption spectroscopy applied to glucose monitoring. I see a question in the chat. What are the main roadblocks that are preventing silicon photonics technology to reach its full potential, especially in medical applications? And is there any preferred polarization for sensing applications? Well, let me take the first one. The main roadblock for medical applications. Well, I think today the main roadblock still is that silicon photonics is still a relatively young technology. It is true to say that, as I mentioned earlier, that you can fall back on existing technology, existing infrastructure, CMOS fabs, etc. That is in principle correct. In practice, there are not so many CMOS fabs around the world that that already have developed a process flow for silicon photonics. It's also true to say that the turnaround time of those that have developed such a process flow is still relatively long. when you make a chip design and you send it to the fab, then you typically have to wait for easily half a year before the chips come back. So the supply chain is not yet fully mature. I think it's a matter of time to come to a more mature supply chain, but today there is definitely, for the companies acting in this space, that is certainly today still a headache. I think that is probably the main roadblock that I see for now. If I think a couple of years out, perhaps 5 years out, I think that main roadblock will be removed. And to be honest, I cannot easily think of a sort of a fundamental roadblock. So I think the future in general is bright for medical devices based on integrated photonics, and in particular based on silicon photonics. The other question is there a preferred polarization for sensing applications? That's an interesting question. Perhaps I should go back a few slides. Or perhaps this slide will do. As I mentioned here, the optical mode that is guided by the waveguide. By the way, I should perhaps mention that these waveguides have sufficiently small dimensions in thickness and width so that they are single mode waveguides. That is quite important because the devices that we are typically using are interferometric in nature. And in such circumstances, you don't want to use a multi-mode waveguide. You really need to use a single mode waveguide. So the dimensions have to be small enough. And in silicon photonics, typically this thickness is a few hundred nanometers thick. And this width here is perhaps typically anywhere between 400 and 1000 nanometers wide, typically. Now, I said single mode devices. The fact is that I'm lying a little bit because such a waveguide is still two-moded, because the single mode that can propagate in this waveguide can come with two types of polarizations for the electric field. There is the TE mode, transverse electric field, where the E field is predominantly horizontal. And there is the TM mode, the transverse magnetic mode, where the E field is predominantly vertical. Both can be used. I think it's generally true to say that in silicon photonics, the TE mode is more popular, but there are cases where the TM mode is being used. And actually, for sensing, you can argue that TM mode can be more promising because these evanescent tails that you see outside the waveguide are actually reaching out further into the cladding in the case of the TM mode than is the case with the TE mode. So there can be advantages to use TM modes in such waveguides. So, but generally there is not a very strongly preferred polarization, I would say, and both are possible. Another question that came in here is, can the sensitivity of glucose detection be made higher, say micro M concentration? I'm not sure what exactly is behind this question, but okay. Well, the problem really that what limits, I'll show this result again, to really go even further down here. That's, I think, what the question is. Can you go to even lower concentrations? You already see that here things become a bit tricky. The difference, there is a single measurement and a replicate measurement here. They differ a bit. When they differ a bit here, that doesn't harm. When they differ here, you're really in the hypoglycemia region. That's a dangerous region for the human body. It's hard to be very accurate. The problem is, and this was glucose in water. If you go to glucose in blood or interstitial fluid in tissue, there are so many factors. I mean, the composition of that blood can be very different. Perhaps the person has drunk some alcohol, for example, or there can be lots of factors of variability. So that is really the reason why taking it to an even much better sensitivity than this 1 millimole is actually very difficult. And I'm not aware of many methods to do that. Perhaps a little bit better than 1 millimole, but not dramatically better. And then the other question here was, please explain the challenges of glucose detection from the blood. Not sure exactly what the question means, but of course the classical way of measuring glucose is to finger prick. Then you have a drop of blood. You have direct access to the blood when you finger prick, and then you put that into a machine that will measure glucose levels. There are many chemical ways of doing that. But if you want to do continuous monitoring every 5 minutes, for example, you don't want to prick a person's finger every 5 minutes, then you need to either have a method that measures completely non-invasively from outside the body without pricking, or you have, as is the case in what I showed here, you need to have a subcutaneous implant. Both methods are being researched massively. There are many initiatives simply because the need is so high. Time will tell whether anybody will develop a reliable, completely non-invasive method. Of course, if non-invasive methods really work well, then perhaps an implant-based method has a problem. But so far, I don't think there are reliable methods in the marketplace based on non-invasive measurement of blood glucose. By the way, if you put this sensor underneath the skin, you don't have direct access to a blood vessel, so you're measuring from the fluid, the so-called interstitial fluid in tissue. But of course, that fluid, a little bit further down, there is a blood vessel, and there is always some transfer of glucose from the blood vessel to the surrounding tissue with a bit of a delay, perhaps a minute or so. But eventually the concentration of glucose in the interstitial fluid is directly linked to the blood glucose level. Okay, let's move on. I'll have to speed up a little bit, I think. A second application case that we are working on is cardiovascular monitoring. Cardiovascular diseases still are the biggest killer in the world. Primary cause of death in the world, over 30%. So quite obviously, whatever you can do to prevent cardiovascular disease or to monitor it carefully, etc., is very important. So here again, our focus is on devices that are point-of-care devices that can be used at home by general practitioners, etc., that would monitor relevant cardiovascular parameters. Now, the most prominent that everybody is measuring all the time is blood pressure, but blood pressure is a very complicated parameter for doctors. That's at least what I understand from them. So blood pressure in its own is not enough to know sufficiently well whether or not there is a risk for cardiovascular disease. And some of these diseases can come very, very sudden. That is obviously a problem. Some of the problems in cardiovascular disease is arterial wall stiffening, arterial sclerosis or atherosclerosis, deposition of plaque on the interior of the arterial walls, also stenosis, narrowing in a blood vessel, etc. So there are all sorts of conditions that you would want to monitor and detect, if at all possible, very, very early. What we are working on is using a technique called laser Doppler vibrometry, which simply maps the movement of skin above arteries. And of course, as we all know all too well, if if you put your finger on the carotid artery, you obviously feel your pulse. So somehow you can detect something of the workings of the arterial system and the heart by just detecting the movement of those arteries, and in particular above the artery at the skin level. One important marker is what is called pulse wave velocity. Pulse wave velocity is the velocity by which upon each heartbeat you generate really a pressure wave into the arteries, and that pressure wave spreads throughout the body through the arteries, and it does that with a certain speed. Typical speeds are 5 to 10 meters per second. That is not, obviously, that is not the blood speed, but it's the speed by which the pressure wave propagates in the arteries. Well, that pressure wave velocity is linked to the arterial stiffness. And typically when people grow older, the arterial walls get stiffer, and therefore that pulse wave velocity will become higher. So what we have been working on is to develop a simple non-invasive device that would measure pulse wave velocity. And we are working on several modalities of this, but here you see one prototype that was tested clinically, where indeed you see this device, and it contains laser beams shining onto the skin above the carotid artery. And indeed, it's based on laser Doppler vibrometry, which I think I explained in the next slide here. In laser Doppler vibrometry, you send a laser beam to a target, and the reflected light is coupled back to the same device. And then with an interferometric technique, you measure the optical path length of this distance between device and the target, in this case, the skin of the patient. And of course, when this moves around, you will typically have a change of that optical path length, which leads to a phase change, which you can detect. We are building silicon photonics-based chips for that, in which we have a chip where laser is hybridly integrated here. Light splits into two arms. One arm is imaged through a lens system onto the skin. Reflected light comes back and is then recombined with the reference arm. And then we have a so-called optical hybrid. That's a little detail here. But eventually we can measure in a set of detectors, we can measure the phase change essentially between the two arms, and that is changing because that the skin here is moving back and forth upon each heartbeat. It boils down to the fact that when the skin moves around, that indeed on the so-called IQ circle, we see this change of the phase of the phase difference between the two arms. Here you see just a schematic drawing of that chip. We do that not just with one channel, but we send out light beams, an array of light beams in parallel. So we hit the skin, in this case, on 6 different locations. That gives us more measurement data and avoids that the doctor has to search for exactly the optimum position. Here you see a picture of those silicon photonics chips that do the job here. But what we built on top of these chips is this little micro optical device that is actually the laser diode here. It goes through a so-called optical isolator, and that is coupled in the silicon photonics chip that is sitting underneath. I will not touch upon all these technical details. But here you see a result for a so-called carotid femoral measurement. Carotid artery is sitting in the neck, femoral artery is sitting in the groin, and of course, when the heart beats, the pulse wave is much quicker here than it is here. And from that delay between the two signals, we can determine the pulse wave velocity. And And indeed, we did measurements against other calibrated methods, and we found a good correspondence between this LDV-based method as compared to the currently used clinical standards. And the advantage of the LDV method really is that it is a device that doesn't have to be in contact with the skin, whereas the existing methods being used clinically are methods where you have to apply transducers to the skin, etc. So we hope to bring this method to a level where it is no longer only used in hospitals, but also be used by general practitioners, for example. Okay, any question on this part? Actually, I see on my clock that my 1 hour has passed. I do have one more subject, and that touches upon Raman spectroscopy, and I hope to bring that as well. So let me ask the organizers whether I can spend another 5 minutes.
Yes, sir.
Okay.
Yes, sir, please.
I have a question here in the chat. Does the nature of skin color texture have an impact on LDV measurements? That's actually a very, very good question. I'll go back to this picture here. In the past, but we want to get rid of it. In the past, you see these little stickers here sitting on the skin. These are so-called retroreflective stickers. They are from the company 3M. They are little patches filled with microscopic balls. They have the property that if light is incident from a certain angle, that the reflected light goes back in the same direction from light was coming. And that's of course very good for having a high efficiency of having light coupled back into the device, which is necessary because it's an interferometric method that we are using here. But of course, yeah, these patches are in clinical practice not so desirable. You need to apply them first. You would hope that you just pick up this device, shine it on the skin, and 30 seconds later, you're done. If you have to apply those patches, you will be working for a few minutes to do that, so that's less desirable. As long as you don't use patches, you don't have to worry about the nature of skin, like skin color. Of course, if you remove the patches, you work patch-free, and that is what we are now developing. You are dependent on properties of the skin. Now, the skin is always quite scattering, and that's actually a problem because reflected light scatters in all directions, and you can only pick up part of it. But indeed, skin color matters, and indeed, dark skin will reflect less than light skin, quite obviously. So that's a problem. Were it not for the fact, and I'm sorry that I don't have a slide about it, were it not for the fact that at certain wavelengths in the infrared, we all look the same, especially at a wavelength of 1300 nanometer. Dark skin and light skin are equally light or dark. I mean, both reflect quite reasonably, about 30%, independent of skin color. So it's interesting to mention, but if we would be living in a world illuminated by 1.3 micron light, and assuming that our eyes would see that, then there would not be such a thing as dark skin or light skin. We would all have the same skin. So we are now developing a new version of this prototype, and it will work at 1300 nanometer for that reason. And we hope that it will work properly without the need of these patches. But with that, I really need to move to my last subject here for today, which is, again, in vitro diagnostics, but now not by refractive index sensing, but by on-chip Raman spectroscopy. As an Indian, I would assume that you all know what the legacy of Sir Raman is. He discovered the Raman effect, which simply says that if light, for example, of a wavelength of 785 nanometer, for example, shines on a molecule, and this should represent ethanol, an ethanol molecule, I think, because of the vibration of the molecule, it's not a stationary object, it's a moving object. Because of the vibrations of the molecule, the scattered light will not only be the same frequency again, but will also show new frequency components. And each frequency component here, for example, this line here, happens at a wavelength such that the frequency difference between the pump and this so-called Stokes wavelength, this frequency difference matches a vibration frequency of that complex three-dimensional mechanical object. And of course, in a typical Raman spectrum, this is actually the Raman spectrum of ethanol. If you shine a laser onto wine or beer or Geneva, and you look carefully at the scattered light, you will see this spectrum. And you will understand that this spectrum is really a fingerprint for a given molecule. Take another molecule, CO2 or methanol or whatever, and you will see another spectrum. Thank you, Mr. Sir Raman. Well, what we are developing is so-called waveguide enhanced Raman spectroscopy, where again we make use of this property that guided mode in a waveguide is partly overlapping in the cladding with the surrounding medium. So if the surrounding medium contains certain molecules from a fluid or from a gas or whatever, and we send in light, that is now our pump, some of the evanescent tails will excite those molecules, and the scattered light, which partly couples back into the waveguide, the scattered light now will have those new wavelengths, and then you send that to a spectrometer, you measure that fingerprint spectrum, and you know what molecule it is, and you can also calibrate it for the density of those molecules. And you can use normal strip waveguides as shown here, but you can also use these so-called slotted waveguides, and slotted waveguides have this interesting property that there is quite a field intensity, not in the two cores of the waveguide, but in between, in this slot, and the slot is filled with our analyte, the medium that we want to measure, where we have a relatively high intensity, and therefore we have, as compared to this waveguide, we will have a much stronger Raman scattered signal. So indeed, the principle is a bit similar to what I showed for reflective index sensing, but now the measurement principle is different. We have a waveguide, we put the fluid on top of the waveguide. In this case, it's a simple example with isopropyl alcohol. And then you analyze the spectrum of the light that comes out. And indeed, here you see this example of this measured spectrum. Then you go to databases of Raman spectra, for example, this, and you can easily figure out that indeed this must be isopropyl alcohol. The big advantage of using waveguides in this context is that waveguides have an integrating effect. I mean, light comes in here and you start to pick up Raman scattered light and more Raman scattered light and more Raman scattered light. So by the waveguide length, you get more and more signal, which is not the case in a conventional Raman microscope. So you can simply make the waveguide longer. Of course, there are waveguide losses, and at some point it doesn't help anymore. But as long as the losses are low enough, you can make the waveguide longer and collect a larger and stronger signal. There is an alternative modality for the same thing, which is plasmonic, where now we use, this is the dielectric waveguide again, but at some point it transitions into a metal slot waveguide, simply a slot between two metal blocks here, typically made of a noble metal such as gold. And it's well known that in a metal slot waveguide, this field enhancement in the slot is even much more spectacular than was the case for a dielectric slot waveguide. So in this case, in very narrow slots, I'm talking now about slots which are just a few tens of nanometer wide, you get a huge electric field enhancement of the guided mode. And it's well known in Raman scattering that the strength of the Raman signals scales with the fourth power of that field enhancement. So with that, you can really boost your Raman signal quite strongly. This is also called surface enhanced Raman scattering. I'll skip this. And indeed, with that technique, we could of certain monolayers that are adsorbed to the gold surface of a molecule called nitrothiophene, we can really measure very rich spectra with many peaks because the enhancement is so strong. We have been using this technique in a number of applications. I'll just touch upon one of those applications. This is biochemistry in a biological context. What we want to do is monitoring of enzymatic activity. What we do in this case is work sort of in a negative way. I mean, we functionalize, this is the metal slot waveguide, we functionalize it with a certain molecule. It's a so-called peptide chain. Peptide chain is a chain of amino acids, such that at some point there is a transition between two types of amino acid such that an enzyme can break it off. And here you see that illustrated, an enzyme such as trypsin, for example, when it comes in the fluid and comes in contact with that metal slot, it will cut off the tail of that peptide chain. And now we make sure that as part of the peptide chain, some of these amino acids have a strong Raman scattering signal, typically the aromatic ones. And of course, because we break off this tail, one of these peaks will disappear. So here we use the disappearance of a Raman peak as a monitor for the presence of the enzyme, and this is being used in studies of cellular expression. Okay, but I think I should really come to a conclusion here in view of time. I think I convinced you to some degree that integrated photonics, chip-based photonics, and in particular silicon photonics, has this potential of serving many medical applications, many modalities of sensing. And I especially emphasize applications where really you could hope to move to a point of care, personal medical devices, in the body devices, and also in vitro diagnostics, where really the value proposition of silicon photonics is compact size and volume, as well as low cost. And I've discussed biosensors, mostly for immunoassays, based on refractive index sensing. This is now in the market. And with COVID-19, there has been really a big boost of new accelerated activity in this field. Not only for optical biosensors, also for other ones, but I'm quite confident that optical biosensors will become quite prominent in this space. But then I've talked about other sensing modalities. There is the continuous glucose monitoring, that's absorption spectroscopy. I talked about pulse wave velocity measurement, that's laser Doppler hydrometry. And I've talked about the more selective detection of medically relevant molecules, which is the weak part of refractive index sensing. Refractive index sensing cannot be very selective unless the absorption mechanism is selective. Whereas, of course, Raman spectroscopy is selective in its own right because it is based on the fingerprint of a spectrum. And with that, I would like to conclude. Quite obviously, this is the work of many. Let me be clear that certainly not the entire group is working towards medical applications. We are working towards many different applications, but sensing in general and also medical is certainly growing in importance. I obviously have to acknowledge funding from many different funding bodies, especially the European ERC and Horizon 2020. To acknowledge the Photonics Research Group and also IISER, because as I've told you in the beginning, they have these beautiful wafer technology platforms in silicon on insulator and silicon nitride, with which we make the chips that I've been talking about. And with that, I would like to conclude.